second section in Unit 7 is about logarithmic functions. To me, logarithmic functions are easily understood if you understand exponential functions. Some people really enjoy them, some people just don't like them at all, but it's something that we use frequently in higher level math and science classes. So this idea of a logarithmic function, it's really important that you understand that it's an inverse of an exponential function. When I say inverse, I mean you're going to switch x and y. So an exponential function is in the form y equals b to the x. And if you remember it from Algebra 2, if you got into that, you would rewrite this as a logarithm, as log base b of y equals x. So the inverse, if I switch x and y, x equals b to the y, and then I write that as a logarithm, I get log base b of x equals y. So that's how it makes sense to me, but that doesn't mean it's going to make sense to you that way. So a logarithmic function is written as f of x is equal to log base b of x. B is a subscript, but b has to be greater than 0 and it cannot equal 1. So if I had y equals log base 2 of 8, this means 2 to the y equals 8, so that y would equal 3. So when you're solving a logarithmic equation, you're looking for the exponent. This 3 is the exponent on the base. So for most people, when you're doing logarithms, it's easier to think about exponents, since that's what you've been using before, and then convert them in from a logarithm to an exponent. So a lot of information coming here. So the first thing is we're going to talk about natural logarithms. The natural logarithms mean the base is just the constant value e that we talked about before. So log base e of something is going to be written as a natural log, ln. On your calculator, it's right here, natural log. So if I turned on the calculator, I type in natural log, I'd have to put a number there. Say I put the natural log of 5. It's going to be a decimal. The other logarithm we talk about often is a common logarithm, and this just means that the base is 10. So if I had log and I wrote a base 10 here, we typically don't write the base, we just call it a common logarithm. And on your calculator, it's right here, the log button. So if I did log of 7, it gives me a number. With technology changing, and even in the last 10 years, the calculators have the ability to do other bases than the natural log and the common logarithm. It used to be where these were the only two forms that you could use a calculator for, and you had to know how to convert to other bases. And using a TI-84, if I go to alpha and window, and I go down to number 5, it says log base, I can hit enter and I could put any base there at all. So we did 2 earlier, log base 2 of 8. I'm looking for the exponent, 2 to what exponent equals 8, and that's going to equal 3. So the calculators made it a lot easier. When we rewrite exponents and logarithms, if we start with a logarithm and we want to rewrite it as an exponent, there's a pattern. So if I had 6 squared equals 36, that's the exponent. Oops, I'm going down to the wrong one. Let me erase that. I'm going ahead of myself. Let's say I had log base 2 of 32 equals 5. What that means in exponential form is 2 to the 5th power equals 32. I'm going to do a few examples here, and it's going to look messy if I don't put these lines here. If I had log base 4 of x equals 3, if I wrote it as an exponent, the base is 4, the exponent is 3, and it's equal to x. If I use a common logarithm, so log base is 10, I don't need to write it, of 1000 equals 3. What that means, I don't write the 10 here, but I have to write it as an exponent. 10 to the 3rd power equals 1000. And the last example I have here, if I have log, the base is 25. The value of 5 is equal to 1/2. If I write that as an exponent, it's going to be 25. My base to my exponent equals my value. And at this time, it's a good thing to talk about this 25 to the 1/2 power. Well, that's just saying the square root of 25 is equal to 5. So when we're using exponents and logarithms, we're going to use rational exponents more than we will use square roots. Now if I start out with an exponent and I want to rewrite it as a logarithm, it's the same process, just reverse order. So my first example would be 6 squared equals 36. That's exponential form. I'm going to write log. My base is 6. The value is 36, and it equals the exponent. Another example, 5 to the x power equals 625. If I rewrote that as a logarithm, I'd have log base 5 of the value 625 is equal to x, which is the exponent. I could do negative exponents. 2 to the negative 1/2 or 2 to the negative 1st power equals 1/2. As a logarithm, it would be log base 2 of 1/2 equals negative 1. Remember, your base cannot be a negative number. In fact, the value inside here, this value here can't be a negative either, and we'll talk about that when we graph these. And I could do another negative exponent. 10 to the negative 2 is equal to 1 over 100. So this is a common logarithm. I don't need to write the base. Log base 10 of the value 1 over 100 equals the exponent. There are properties with exponential functions also, and I'm not a big fan of saying you have to memorize properties, but these properties are very important. They're going to come up often, and they're going to make your life easier. When I say log base b of b equals 1, what that means is b to the 1st equals b. So if I've taken the exponent, or taken the logarithm and rewrite it as an exponent, this should make sense to you, but that's what that property is saying. So for example, I'd have log base 7 of 7 equals 1, because 7 to the 1st power equals 7. And it doesn't matter how big the base is. Log, if this was a 342, this was a 342, the exponent's going to be a 1. Another property is log base b, b to the nth power is going to equal n. If I rewrite this logarithm as an exponent, I have the base is b to the nth power is equal b to the n. Well, that makes sense. See what it looks like with numbers. If I had log base 6, 6 to the 4th power, that means this is going to equal 4. when we do some expanding and condensing, I can show you how that works that way too. If I had log 10 to the negative 5. Now remember, I didn't write the base here. The base is a 10. So that means this is going to equal negative 5. And the last property for today, log base b of 1 equals 0. No matter what the base is, if you take the log of 1, it's always going to equal 0 because b to the 0 power is equal to 1. Anything to the 0 power is equal to 1. So these logarithmic properties come from the exponential equivalent. So if I had log base 9 of 1, it's going to equal 0. If I had common log of 1, it's going to equal 0. And if I did a natural log of 1 equals 0. Now let's discuss a little bit with the graphs. In an exponential function, the domain was always all real numbers. Well, since we're switching x and y, so exponential functions, you have x, y. My domain was all real numbers. It helps if I move that up and you can see it. So an exponential function, my point x, y, my domain was all real numbers. My range was from the asymptote to infinity. So that means in my logarithmic function, I'm switching x and y. I'm switching my domain and range. So my range of every logarithmic function is going to be negative infinity to infinity, without a doubt. My domain is going to go from the asymptote to infinity. So most logarithmic functions start out like this. Instead of going to the point 0, 1, it's going to go through the point 1, 0. And it's going to have a vertical asymptote. So we have a vertical asymptote. So this a specific graph, my domain would be from 0 to infinity. If I move it up or down, it's not going to change my domain, but if I move it right and left, it will move my domain. So let's look at the vertical asymptotes. Exponential functions had horizontal asymptotes. If I'm switching x and y, I'm switching my verticals and my horizontals. So as a logarithmic function approaches a specific x value, the function will approach negative infinity or infinity. So if I give you an example, if I have y equals log base 3 of x, I'm always going to go through this point 0, 1. Log base 3 of x looks like this. And my vertical asymptote is x equals 0. Well, let's change this. Let's do a transformation. What if I did this as y equals log base 3 of x plus 2? That's going to move this left 2. So instead of x equals 0, my vertical asymptote is going to be x equals negative 2. Actually, I did that wrong. Let's make this correct. I was thinking my y-intercept. My vertical asymptote is x equals negative 2. That's my y-intercept. And it looks like that. If I had a common logarithm, and I'm not putting a scale on this on the y-axis. Common logarithm, it's still going to go through the point 1, 0. Looks like that. It has a vertical asymptote right there, so at x equals 0. But then when it changes, y equals log of x and then plus 4. That's going to move this up 4. Well, if that moves this up 4, it didn't move it right or left or anything. My vertical asymptote stayed the same. And makes people uncomfortable, but let's look at a natural log of x. We're not even going to put the y values here. It's still going to go through the point 0, 1. It still has this vertical asymptote at x equals 0. But then when it change this to y equals natural log of x minus 1, this is going to move right 1. So if it moves right 1, it's going to move my asymptote right 1, and it moves my y-intercept, or x-intercept, right 1. So to find the asymptotes, it's really easier to think about these as transformations. A basic parent function logarithm is going to have a vertical asymptote at x equals 0. If you move that graph up or down, it doesn't change the vertical asymptote. If you move it right or left, it will. So, to summarize transformations, vertical transformations mean I'm going to move up or down. So this is going to be up C. Minus C is going to be down C. But the problem that happens with this is I didn't put parentheses around here. I do on the next one. But that gets confusing. So you might want to write this as y equals C plus log b of x. Log base b of x. And this would be y equals negative c plus log base b of x. And if it's written like that, it's a little bit easier to see that this is going up and this is going down. If you put a number with the x, it's going to move it right or left. So this x minus c that's in parentheses is going to go right c. Plus c inside with the x is going to go left c. If you change the sign of the x value, just like an exponential function, if I change a 1 to a negative 1, it's going to flip over the y-axis. So it's a y-axis reflection. Negative out in front is going to be an x-axis reflection. And once again, I'm not talking about vertical stretches or shrinks or horizontal stretches or shrinks. My main goal is that you understand just these basic transformations. So once again, let's look at a logarithmic function. This is log base b of x, but I have to choose a value for b. I can't graph that on here because b is just, it's a variable. I need a number. So I'm going to let b equal 2. So that means I have y equals log base 2 of x. And I can do a table of values again. If I had y equals log base 2 of x, let's go ahead and I can't pick a negative number. So I can't use negative 2 and I can't use negative 1. I can't even use 0. I mean, if I put a 0 in here, log base 2 of 0 doesn't make any sense. 2 to what power equals 0? It doesn't matter what exponent I put there, I'm never going to give a 0. So I'm not going to have anything there. That's how I get my asymptote. I cannot get a value, so this is my asymptote. If I put a 1 here, y equals log base 2 of 1. Well, that's a property. 2 to what power equals 1? Well, it's always 0. So that's where I get this point. And I will always have that point. What if I had y equals log base 2 of 2? Well, there's another property. Log base 2 of 2 is going to equal 1. So if I put a 2 in for x, I'm going to get a 1 for y. Log base 2. If I did 3, I'm going to get a decimal. I don't want to worry about that. I'd rather plot integers. So let's go to the next one. Log base 2 of 4. 2 to what power equals 4? Well, 2 squared equals 4. So 4 is the x, 2 is my exponent. So I'm going to plot the point 4, 2. And if I did this again, I would skip 5, 6, 7. The next one that's going to be nice number is 8. Log base 2 of 8. So 8 is my x value. I'm looking for the exponent. 2 to what power equals 8? 2 to the third power equals 8. So I'd plot the point 8, 3. Just like an exponential function, I could keep getting closer and closer to this asymptote. So I have to show it by continuing that line. If I graph it, that's why I don't like you picking up a calculator. If I want to graph this, alpha window, fifth one down, log base 2 of x. It doesn't really graph it. You cannot see it. I can take away my axes. It looks like it stops there, but it doesn't stop there. So the calculator is misleading. That's how I know if somebody's picked up a calculator to graph it and they don't understand what they're doing. I can go to my table of values and I can see I've got errors. I cannot go below 0, and it gives me all the numbers that I just created. So if log base 2 of 8 equals 3, the next number that's going to be an integer should be 16. There it is. Because 16, log base 2 of 16 equals 4, or 2 to the 4th power equals 16. So on this logarithmic function, my domain is from 0 to infinity. My range is the same range for every logarithmic function, negative infinity to infinity. My x-intercept is going to be the point 1, 0. If I were to draw my logarithmic function or my exponential function on here, this is what my exponential function, 0, 1. Instead of 2, 1, I'd have 1, 2. Instead of 4, 2, I'd have 2, 4. Instead of 8, 3, I'd have 3, 8. There's my exponential function. They are inverses because they're a reflection over this line, y equals x. And we did this in this course earlier, if you remember. And we did composition of functions. And if compositions of functions f of g of x were equal to x and g of f of x were equal to x, that they were inverses. Let's do just a few examples. So my first one I want to do is y equals log base 2 of x plus 5. So log base 2 of x plus 5. That's going to move left 5. So I'm going to take my asymptote and move it left 5. I'm going to take this point 1, 0 and move it left 5. 2, 1, move it left 5. 4, 2, and move it left 5. So my domain is from negative 5 to infinity. My range is all real numbers. My asymptote is x equals negative 5. And my x-intercept is negative 4, 0. The next example I'm going to do is y equals 3 plus log base 2 of x. I prefer it written like this. It's just easier for me to see that I know this goes up 3. So if it goes up 3, my asymptote doesn't change. But I'm going to take this point 1, 0 and go up 3. 2, 1 and go up 3. 4, 2 and I'm going to go up 3. So you can see my domain is from 0 to infinity. My asymptote did not change. Oh, my x-intercept did. To get my x-intercept, I would have 0 equals 3 plus log base 2 of x. Later on, I'll teach you how to solve that. And then I would get 1/8. And I'll teach you how to solve that later on. The last example, y equals negative log base 2 of x. So that's going to be an x-axis reflection. So if it's reflecting over the x-axis, my vertical asymptote stays the same. The point 1, 0 stays right on the x-axis, 1, 0. This point 2, 1 is going to be 2, negative 1. This point 4, 2 is going to be 4, negative 2. So that's an x-axis reflection. So my domain doesn't change. It only changes if I move right or left. My range is still all real numbers. My vertical asymptote is still the same. And my x-intercept is still the same. So we're going to practice these. Please don't pick up a calculator. If you want to use a calculator to get the points, I can understand that. But the graph gets distorted with a calculator. So don't pick up a calculator to do these.